My name is Niklas. This is Alexander. We are going to talk about something that we wanted to implement for a long time, which is the device manifest. My name is Niklas, as I've said. I'm an embedded software engineer for a long time. I studied computer science in Germany somewhere, and then I did autonomous robots for a while. I maintain an open source C++23 embedded library that you might find interesting. I worked briefly at ARM for like 2 years, and then I did the most important project of my life, which is a scale model of German railway signals. Ask me about it. It's very fun. And now I started working at Auterion in almost 3 years ago. That's a long time. Yes.
Yes, hi, I'm Alex, also a senior software engineer at Auterion, also from Germany, also studied in Germany, so very similar. But previously I worked in automotive. I was at Vector Informatik, did a bit of real-time operating system in automotive context. Then I switched over to Mercedes-Benz, did work still embedded software, but in a security context. And now I'm at Auterion and doing PX4 drivers. Basically everything related to low-level drivers, fixing bugs and nuttigs like TXDMI getting stuck, and occasionally I help out in Mufflink and also the DDS client, but mostly working on low-level embedded software. So let's get started on what we want to talk about today. So what we want to talk about today is a problem that some of you guys might already face. We have a nice picture here. On the left side, you will see the state that you want. You start up your drone and you see the thing on the left. When you have a look at the driver output, you see that it's running, everything is working, your topic is published, and basically the driver works as expected. From sometimes you will actually see then the picture on the right where the driver is not running for some reason. And then you don't have the information you need, like in this case from a magnetometer. And this can be very sporadic. That's not a problem if you have just one drone. But if you have thousands, sporadic issues will happen very, very often. And then you have a silent sort of failure as the external magnetometer in this case is not working. The reasons for that can be quite hard to debug. It can be power issues, it can be EMI or similar things. Then you try to debug and find out why all of this happens, and then you will see this interesting code on the left, where for some reason you see that hundreds of magnetometers are getting started, and you wonder why we do it like this. And yeah, basically we have opportunistic drivers starting in PX4, where we start a whole bunch of drivers and see what sticks. Yes, and that is of course prone to error, as we don't know what drivers should be started. We just start all of them. They execute the probe function, for example, the one you see on the right, where we try to see if the driver is actually there. And this type of architecture works most of the time, but it does not work, for example, when you have bad communication due to EMI, or when the power architecture you have first starts the flight controller and then the sensors, because then the probe function will fail and the driver will not start. We want to solve this problem, of course, because this is a system that's not reliable enough, because you have drivers that sometimes start, sometimes don't. So we want to set up a system that solves this, and we thought about requirements on how this should look like. So the very rough idea what we need is sort of describe what hardware is actually on the drone. And we want to have then the option for the developers to access this information. So what we need is a very easy to use setup where the developers can access which hardware is actually connected to the drone. We want the integrators to be able to describe this in an easy ways. And we also want the pilots to be able to dynamically configure this, so you can quickly change the drivers that are the sensors that are connected. The whole system we want to set up is a bit complex, so we want it to be very extensible, so you can easily then also describe different pieces of hardware. And what we also want to solve is another problem you see currently, that you can't really start multiple instances of the same drivers currently, as all of them share the same parameters. So we want to solve a lot of things, and in addition we want to ensure that all of this doesn't use a lot of flash, because we already don't have flash anymore. And on top of that, it should, of course, be backwards compatible. So yeah, a lot of requirements that we set ourselves. So now over to Niklas on what and how we actually want to do this.
Yes, so Alex already mentioned parameters. So we want to do something with the PX4 parameters. Specifically, we need to configure quite a lot of things for each driver to configure the I2C bus, for example, which I2C bus, which port is it running on? We need to set the speeds. We need to set physical properties like the rotation. We need to know some sampling settings, filtering settings for a lot of sensors. And this needs to be saved across reboots, and it needs to be configurable remotely because you don't want to open up or use the CLI or something like this. So there needs to be a user-friendly thing. And we have that. It's called PX4 parameters. It gets tunneled over Mavlink. It gets tunneled over DroneCon. So the basic idea is to store the manifest in the PX4 parameters, and then at runtime, auto start the relevant drivers and then supervise their health. But it's not ready, and it doesn't work the way it's currently implemented. So what we're going to do is break PX4 parameters. You're all excited. So please hold your tomatoes until after the talk. So
yes, now let's go to what we actually need. So basically the idea is that we want to describe the whole hardware that is attached to the drone in PX4 parameters. And as you all know, a PX4 parameter can only store an int or a float and only 32 bits of information. So that is not enough to, for example, describe, in this example, a power module, where you need to configure how much current it can handle, how the shunt is set, which I2C bus it should run on, and things like that. So we need to store a lot of information to have a PX4 device manifest. So what we want to have is a very generalized system where you can store arbitrary data in the PX4 parameters. We want that system to be able to store more than 32 bits. So what we came up with is this thing you see on the left. So basically you have a language where you describe what you want to store. In this example, for a power module, we store the current it has, the max current it supports, the shunt, and we also store general I2C information, like on which bus to start it on and on which address, which I2C address. This is also general stuff that a lot of drivers will need. So we have a sort of default set of descriptions. And the idea is then to have these descriptions for every driver, what the driver needs to know to start up, generate C code out of it so that the user can easily access this kind of information. And then it gets easy because then the driver knows how it started, on which I2C bus it should start, on which address it should start. And PX4 knows which hardware is attached and doesn't need to guess which drivers it should start. And then we can also do health checks because we have the ground truth of what to expect. And if drivers don't start, we know that we should report errors and don't have silent failures anymore. So then we had basically had an abstract description, and then we thought it's pretty a lot of work to actually serialize all of that stuff, and we don't want to write a compiler for our general parameter definition language. And then we luckily found DroneCon, which solves all of these problems already, because they also have messages that they need to serialize. So what it did is just use the DroneCon serialization logic, as it's already there and it already works. We can use the serialization rules of it. It's very nicely, very neatly done by them. It is very efficient, uses bit fields. There's no wasted storage there. And the rules which it serializes it are also well defined, so it does work on each platform. There's no assumption on the platform. And in comparison to the current version that's used in PX4, the new libcanard, which can be used to serialize and deserialize all of that data, is also very efficient. It doesn't use all of that template logic that is currently used in PX4. So it's pretty small, and that's nice for our use case.
So how we mentioned that we now have the first part of the solution, so the actual packing of the parameters, the content of the parameters, but we also need to have one parameter per driver instance that we want to start, and this is currently not implemented. Parameters are quite static. So to start multiple drivers, we need to allow parameters to be instantiated more than once. And to access the specific instance in the CLI, for example, we can suffix the parameter with a hashtag and a number. This is also how it's done, for example, in UORB. The instances are also hashtag numbers, so it's somewhat consistent. But now you must add an instance. So you must add hashtag 0 for the first instance, for example, to start a driver. There is no default instance anymore. And this is how PX4 knows that the device exists on the drone. We will see later that this can be implemented backwards compatible.
So yeah, just to get a rough picture of how all of this should work. As you saw in 2 slides before, you describe for each driver which information it needs for startup. And then we have a compiler that generates multiple files. First of all, it generates the structures, as you can see in the top picture. This is then the information that the driver can access, for example, which I2C bus it should start on. And what we also do is we generate code for the ground control, because the ground control also needs to know what the parameter actually represents, so it can correctly deserialize the information, because otherwise you would just see some random number in the ground control. You wouldn't know what it means. But with the information you see on the low side, the ground control can do the same deserialization as the PX4 can do. So how does all of this look like? How does the generated code look like? It's actually quite easy to use, because you don't need to care about the parameters at all then. What you get is something like you can see here. You just have the generated structure out of the domain-specific description language, and you can load arbitrary data from parameters into those structures. And it also works the other way around. You can then store this structure into the parameter. And using that information is quite easy, as can be seen in the third piece of code. You just then use the structure as you would anyway use it in C. So yes, it's quite easy to use the system then. What you also need to do is then, to keep the current workflow up, is still allow integrators in the airframe to set up where the hardware is running, because you don't want the pilot to do this. You have an airframe and you know what hardware you connected to it. And that's still pretty easy, as can be seen in this image. You just have then an index-based access where you can set the individual field of the struct. Like in this example, index 5 is the 200 amperes that the power module can handle. It would be nicer to have the actual strings, so you could do a param set default ina238 dot current 200, but we tried this and it uses way too much flash, because then you need to store the string of each field into flash, and we don't have enough flash for that. But yes, what we also have is automatic versioning of all of that stuff, so that when you change the data encoded in parameters, we can do an automatic translation. But that's all transparent. The user does not need to handle that. It's all done in the generated code. So how this looks like then in the ground control, as you saw in the slide before, we also generate code for the ground control. And when you then click on one of those new advanced parameters, it's pretty easy. Ground control can deserialize the complex parameter into the individual parts, and the pilot can then quickly change what bus, for example, the sensor he connected on is. So that's basically the same as it's now, but it's way more compact, as we don't read one parameter for everything, but have a very, very compact representation of a lot of information using bit fields. The actual encoding and decoding in the ground control is the same as it is in PX4. We just use libcanat there, so that's not too complex.
So the actual auto starting of the drivers in PX4 is split into a compile time and a runtime component. in the build system, we tell CMake that we want to auto start this driver. It supports auto starting, and then it just generates a script in nshell in the airframe files that gets called, and it calls every driver with the auto subcommand. And then this auto subcommand is implemented in PX4 by reading the parameter instances, which is the second thing down there, and then destructuring the parameter, and then using this information to start the driver. And then it also passes along the parameter instance to the driver, so you can still update the driver at runtime without rebooting PX4, if that's possible in the driver. So it's pretty much exactly how it's implemented now. Now you can also have some parameters that you have to reboot, or you can change them at runtime and change the driver settings without rebooting. So all of this is preserved. For monitoring the driver, we register the driver with the commander, with the arming checks, for example, during the starting of the driver, and then we delegate the responsibility of understanding what the current state of the driver is in regards to arming or whatever other check we need to do. And this is currently not implemented that way. At the moment, all of this is centralized in the arming checks in the commander, and it's a bit of a spaghetti code. And we want to pull this out a little bit into the driver again, explicitly into the driver. For general health monitoring, we kind of already have a fairly good system, which is called the perf counters, the performance counters. And they do, like, for example, down here, when the I2C fails, then a counter gets incremented. The main issue with this is that it's not really streamed to ulog. You have a pre-flight perf counter, which is saved in the ulog format, and then you have a post-flight perf counter, which is saved after the flight. The obvious problem with this is if the drone crashes, you don't necessarily get a post-flight perf counter. And so we've had cases where it's been difficult to point to issues in sensor drivers where you have to sort of look at other indicators like the attitude or estimator inputs becoming irregular, and then say, okay, probably the driver had some kind of electrical issue or power issues, but that's not very specific. So the health monitoring here is kind of already there, but we need to actually focus a bit more on this. And let's talk briefly about, so we didn't implement all of this. We looked at specifically what the bottlenecks are, and then we implemented small proof of concepts. So we're not breaking your parameters just yet, but there is a backward compatible way of upgrading this. For DroneCon, for example, DroneCon exposes the PX4 parameters over CAN to the DroneCon GUI, for example, and it works fairly similar to how Mavlink does it, but it doesn't have the 16-byte limitation on the name. It has a 128-byte limitation on the name. It also can transfer 64 bits of data. So by just concatenating the instance with the subfield name, we can expose a bunch of parameters in DroneCon natively without having to upgrade the GUI. And so it's going to be a long parameter name, but it works. If you have a 32-bit integer, it will be shortened into whatever your field is. If you have a float, it will be shortened into that subfield. So this is a way to do this in a backward compatible way. Of course, in Mavlink, none of this works because Mavlink is limited to 16 characters. And so you will have naming conflicts with parameters when they get quite long. And so instead, we're just going to enumerate them. So it's not great for usability. You have to look into the documentation, which subfield you're looking at, but it is a way to bridge the gap while the ground stations get updated with this new concept, and it doesn't break the entire configuration flow. There are some limitations. Mavlink only supports 32 bits, so every subfield that we're going to add has to be less than 32 bits. during the transition period. And we are not storing the subfield names with this method either. So in the drone CAN nodes, the CAN nodes that are PX4 based, we usually have more flash available. So there we can store the subfield names to generate the parameters. But for PX4, we're not going to do that.
So yeah, how can we continue there? So we started on a lot of work and there's still a lot of stuff to do. Here's the idea how to roll out of this. We started on the domain-specific data language and the runtime API. Some parts of it are already implemented. That's the first part that we can roll out in a pull request, as it doesn't break anything yet. The same with the automatic driver starting and health monitoring. We started on those already. We can roll them out. In addition, the changes to QGroundControl are needed. You already saw it in the screenshots before. We already started also there, but as with the other points, still a lot of work to do. And then we need to, of course, update the documentation. All of those parts are not breaking, as they don't change the current parameters. They just roll out additional functionality. Regarding the breaking change is, of course, the parameters behave differently. Not all of them, just the ones that we migrate. If we don't migrate them, everything stays the same. But for example, for the power modules, we would really get a lot by starting to roll out the change there, because then you can, for example, start multiple power modules with different shunt values. For example, a problem we see a lot, also an issue up there. So what we will do, we'll do some internal dogfooding at Auterion to test this out, to get some feedback, how it's working. And then if we really change the parameters, there's an update needed, as then the semantic is not the same anymore. So we'll start with some parameters, try out how it works. And then we can start implementing the changes in the drivers also. There are still some limitations, as Niklas said, the 32-bit rule for muffling. And yes, the biggest change regarding user experience here is that you then need to describe what is actually on your drone. Because currently you can just connect some magnetometer, and most of the times the automatic probing will detect it and it will just work. But it will work 100 times, and at the 101st time it does not work. So yeah, that's the biggest change regarding usability. You have to describe then what is attached to your drone, because otherwise there's no reliable way to start drivers. So that's everything from our talk. Thanks a lot for listening. And if you have any questions, feel free to raise them.
Since we are introducing new parameters, does it have any noticeable effect on like the FRAM or EEPROM size requirements?
Yeah, so that's basically what we optimized for, to decrease the flash as much as possible. So that's, for example, the reason why we don't encode any field names. So what you have is, per parameter that you introduce in the previous legacy system, it costs you around 100 bytes, one new parameter, roundabout. So if you have the compact solution we have there, we did some calculations. If you just encode 2 or 3 things into this compact parameters instead of using 5 for stuff like we do now, it already is cheaper to use the compacted version. Even with all the metadata, it doesn't use as much data as it's currently used for describing it, because currently you have to pay always around about 100 bytes per parameter.
So that was actually my question, but I've got another. If you mentioned bringing in libcanard, are we going to have libuavcan and libcanard, or transition completely? In which case, that's kind of another project.
Yes, it would be really nice to transition to libcanard also for our general UAVcan implementation, because the old one is template based and it uses an absurd amount of flash. We tried the new libcanard. It's really, really nice. It's implemented in a very nice way. It doesn't generate hundreds of templates, which causes huge flash usage. And yeah, we should combine those efforts.
Cool, thanks.
Any more questions?
And just one general note from our side, embedded PX4 is quite interesting, and we need a lot of people. And we have the need for PX4 embedded engineers. So if you know someone or want to join us, we need a lot of embedded effort, because that's one of the parts of PX4 where there's a real need for more people to get stuff like this rolled out.
All right. Well, thank you so much, guys.